Another draft physics video production. Comments and then maybe some Leonard Susskind video to just be as a background for explaining where they went wrong, kind of thing, and whatnot. So, might do, well, we'll see. But comments first, mostly Ken Wheeler stuff and whatever. Ken is a Donald Trump of physics and photography. I don't think he really is. It's not like he inherited it. Um, you so obviously he's generated, a following on YouTube talking shit, and people want to hear shit. Anyway, he thinks he knows everything, yet is a simple buffoon who rarely leaves his basement except to get attention. So I don't think any of that's true. I don't think he's a simple buffoon. Um, I don't even think he's stupid, in the simple sense of stupid. He's just a kind of a psychotic nerd. He's got this grandiose perception that because he knows how to translate some dead languages that he's, onto something, or he's magnificent or something, or better than everybody else, or some kind of crap like that. And it doesn't work that way. That he can think no wrong when he doesn't really use a logical process to do much of what he does. Like his magical magnet drain cleaner. remember his magical drain cleaner, and then he had all his pipes replaced. Kind of funny. Anyway, so I don't know. That's not at all how Donald Trump is. I don't know. That's not all how Ken is. Your YouTube content, on the other hand. So he's talking to somebody else's content. Mark Summers. Let's see what his content is. I didn't know any of these commenters ever have content. Oh, he doesn't have any. So, I don't know what that means. Anyway. Misanthropic clown. It's our dumbed down America. That's the tricky part, though. There's no generation that looks too smart. The 20s, you had the roaring 20s, people seem to get it. God is dead. They seem pretty philosophical. And then by the 40s, they're back in long skirts, being nerdy. And by the 50s, their anuses are so tight, that Elvis Presley scares them. It's just strange how the generations turn. So I don't know what to say about that. And then we land on the moon and all that stuff. That's, it is kind of funny. And then we go into disco, and people do seem to get dumber for some reason. Mine was the last good generation. Yeah. Wheeler's acolytes clearly barely finished high school. Well, technically, I could be thrown in that category. Not really. I barely finished. Well, I didn't really barely finish. I finished average, but I didn't try very hard. I guess you can't say I barely finished. I got accepted at a couple of good colleges. Anyway, and certainly not of trig and geometry. So again, this argument that somehow trig and geometry gives you the capacity to understand that start talking about bent space or entanglement, all this kind of crap, all this wooey shit that's in regular physics. At least Ken's smart enough to figure out, well, they don't have anything for that. There's no rational explanation for this crap. Saying something like virtual photon ain't a frickin' answer. But again, his answer is insane. So what good is it? It's dumb and dumber, clearly. Ever actually listen to Trump? He knows nothing but thinks he's a genius. 6 bankruptcies. Yes, he lost more money than he was given. There's not much you can say. He should be worth, if the father just put the money in a trust, the trust would be worth, 10 or 12 billion dollars by now. So Trump has lost it all, essentially. No one said Trump wasn't a moron, but he ain't hiding a fucking basement either. Either's Ken Wheeler. I'm the guy in the basement, frankly. I I just don't see any relevancy in these kind of attacks. You know, I do it too. I mean, I talk about him being fat, but that's mostly because he keeps pointing it out. If he didn't keep pointing it out, I wouldn't feel comfortable saying, "Yeah, you are fat. You're really fat." So what are you going to say? So whatever, useless tripe, pretty much. Just want to say your channel is seriously underrated, exposing the BS spread by people like Ken. How many red flags do people need? I don't know. To understand that he's not providing anything rational. I mean, you can't grok any of it. You can't put any of it. You can't draw pictures of it even. I mean, all you can do is draw spirograph pictures, and I guess that's what people want the universes to be, is some kind of spark. It comes off magic wands. When you tap the magic wand on something, it makes a little hyperboloid. I guess that's what they figure the universe should be. People need to figure out he's full of crap. He's using word soup of non-specifics, refuses to explain anything. Well, yeah, and he's just a despicable coward talking about how, I won all these debates and I always win, and you ever say this to somebody, you ever say that to somebody, he doesn't prove they don't have answers. Call some of the smartest people that ever lived morons. Well, yeah, and it's just so, and his excuse is, as he provides in the video, Tesla did it. So he says, not me calling Einstein an idiot, Tesla did. Which showed how low Tesla's character was, frankly. Either because of mistakes or because he just doesn't like them. Claims everything is so simple yet won't ever explain in simple ways. Yeah, it can't possibly use common vocabulary. Asks for money basically every video, promises to explain things but never actually does. He never-ending repetition of words that don't mean anything, as if Ken's preaching, well, they do mean something, but they don't mean anything when strung together without a context. Preaching to his cult followers, and yeah, that's all it comes down to. And whatever his followers are mostly made out of is photographers, so you got to say there's something seriously wrong, with photographers. Ken is basically an obscuritist, total fraud, which is easily the most intellectually dishonest person a person can be who claims to be a scientist. Well, he clearly commits frauds in his experiments, and that's just a fact. He knows how this stupid supercell works. It's not doing anything super. It's doing something, it's a piece of trickery. It's something a magician would use, not something somebody looking for the truth would use. Science is about hypothesis, prediction, and observation. I don't think it's about those stupid things either. It's about explaining, okay? It's about modeling. That's what science is. Science is basically saying, I'm going to give you a set of facts, or a set of ideas or concepts, or I'm going to string a bunch of words together that fit. It's a description of reality. And that's not what any of this stuff is. Science is description. Experimentation, conclusions, and debates. Yes, so some of these words you can keep, but most of them are crap. And Ken, well, he just plain insane, really. I regret having searched for anti-gravity on YouTube, because now YouTube keeps recommending me all of his bullshit videos. That's must be why his channel gets views. Well, it's an unfortunate fact of us choosing Google as the search mechanism for the internet. It's a popularity engine, not a relevancy engine. It doesn't find the gold, it just promotes the fat kind of thing. It just finds the stuff that's gone viral for a silly lowest common denominator reason. Homer Simpson kept pressing the play button, and so you're going to be stuck watching it. Clickbait all over the place. Yep, he does. Anyone believe Ken Willer's word salad? How does anyone? It's not, you gotta put a question mark after a question. Just saying. Yeah, there's nothing more to say. It's just unfortunate that people really they clearly just don't want the truth, because I just don't think they would accept the same kind of bullshit from somebody else on some other subject. They'd be like, what do you mean? That's not an answer. So they clearly want the conclusion, whatever it is, some ambiguous conclusion that reality, there's not one of those old gods. There's like a different kind of god, and the universe is being controlled by something, but who knows what the fuck that is. I'm really sick of you and Ken in this pissing contest. Well, life is a pissing contest. I'm sorry if you're sick of it, but that's what you're on, the planet of pissing contests. And you're just too wimpy, okay? You got too little small a dick, and you just don't want to play pissing contests. Well, I'm sorry, but that's the nature of the planet, shithead. You both badmouthed Tesla, and Tesla did plenty of badmouthing himself. So, again, where have you shown how it's done correctly? Where have you shown us the model of right to contrast with this model of wrong? Oh, that's right, you haven't. Now that's just wrong. Well, I mean, it's just idiotic not to. Tesla was, in fact, wrong. He proved it with $1 million experiments. And he proved it himself. He proved he was wrong. For fuck's sake. Have you or Ken invented anything that helped mankind? Let's understand, Tesla was in the age of invention, okay? And he was so far in the number of inventions, he was way, 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 way behind in that pissing contest with all these other people like Edison that he badmouthed also. Well, he didn't really badmouth Edison, that's the joke. Except to call him sweaty, which Edison would have said, yeah, that's right, because I work. Or, yeah, I don't just sit around going, twiddle, twiddle, what can I think of today? Yeah. So, yeah, they were obviously opposite people. Tesla said, oh, no, don't get physical till you have to. And Edison was, beat the hell out of it until it does what you want it to do, Invention is 99% perspiration and 1% inspiration. And Tesla was the 99% inspiration guy. And we saw who won that contest. I'm just saying, I mean, the list of real inventions that Edison created, ones that work, how many of their patents, if you were to, tie their patents to actual inventions, how many of Edison's patents didn't work? Oh, probably none. Okay, Tesla was a guy patenting every thought he had, atomic farts. Yeah, I'll patent that. You both spew your parroted BS. Well, again, it doesn't make any sense. Where exactly? Who am I parroting, asshole? See, I mean, you can't get anything right, retard. This is an idiot who calls himself Planet President. And has some little green recycle-y thing. You're like, oh yeah, sure. It's going to solve the problem. Yet neither of you have built anything. Well, clearly, Ken Wheeler invents little gadgets all the time. Perfectly valid. He takes some existing thing and modifies and makes it better. He does it all the time. And frankly, I have plenty of little stuff in my world, but I've clearly provided a model, an invention, all right, that actually unifies physics. It does what Einstein spent his life trying to do. So I don't have to, qualify myself to you. I am going to be, in fact, proven right, and you are, in fact, going to be proven an asshole. There you go. So thank you for making it clear, Planet President. To the future. Make sure Planet President's relatives and ancestors and cruddy little spawn, make sure they all know how dumb Planet President was. I'm impressed by what you've done. What does that mean? I'm impressed by what you've done, not the BS you spew. So, is that a generic statement? Like, I'm only impressed by what you've done. So he should have made it more third-person-y. Both of you need to prove the BS is real. Well, nobody can prove some of these theoretical contentions because guess what? The stuff is too small and you can't take a picture of it and rub it in your fucking dumb ass face. the way you prove it is through logical argument. And I've provided, I think, the proof in the sense that my theory, my model, consistently works everywhere, okay, and it's simpler. So it does more than theirs does. Theirs can't even, theirs can't do gravity and magnetism. Everything has to have separate rules for all the separate phenomenon. Mine does all of it, and doesn't need any entanglement. It doesn't need any 110 magical particles, and it doesn't need any of that shit. The stuff that only exists for a microsecond. Why would stuff that only exists for a microsecond be somehow relevant to your day-to-day life? I don't think so. Israel, show us something instead of trying to impress us with your words. So again, I don't know, what word am I trying to impress you with? Logic? Is that it? Oh, yeah. I think I'll just delete you because you're an idiot. So just remember, planet president. Yes. Yeah, beat him up in the future. This is an idiot. Just a little shit talker. Alright, Eric P. Dullard, your opinion. What do you want? It's like any dissident. He officially has earned a big giant tinfoil hat. What can you say? There's no theory, okay? The theory is some kind of, Tesla said there's all this energy we can just grab, and so they want to go out and find it, and they keep thinking there's got to be a way it's there because somehow Tesla proved it was there when Tesla never proved any of it, never demonstrated any of it. And so he's just some asshole chasing a wrong theory. So he's going back to Heaviside and all the old 100-year-old ideas, okay, of how it works. And they sort of deserve to be 100-year-old ideas, but they were wrong. Dielectricity. It's an idiotic concept. Electricity is one phenomenon. It isn't a whole bunch of phenomenons. You can't have different varieties of it. Simply an observation, no more. Well, whatever that means. Ken Nags NDT, I don't know who that is, and others who are much more famous than him. Ken gets 10,000 views. You nag Ken and get views in the low hundreds. My view count has absolutely nothing to do with Ken Wheeler. Ugh. If you assume that you, Ken, NDT, and company, I don't know what that means, period. If you assume you greater than, Ken greater than NDT, I don't know what that means. Yet the views follow this pattern that say about how fucked society is. Trump is president. You don't need to say any more than that. And there's imbeciles again running against him. Like, we can't find anybody to be president. The president has to somehow be this stupid lying sack of dirty shit. We can't find one pair of clean underwear in this country. Not that I'm one pair even, right? I mean, I couldn't run for president. I mean, I have too many bodies in the closet and all that crap. So, but whatever. If you can't beat them, join them. POV then. It gives a clue about how to succeed in this society. Whatever. The clue on how to succeed was always to be a bullshitter. I mean, that's been true for probably 1,000 years. But whatever. Tell people what they want to hear. That works better than telling them what they don't want to hear. Yeah, duh. Alright, so these comments aren't worth much. Thanks. Not? Yeah. Alright, so we'll play some of this Susskind. I think we'll just talk about electrons maybe, but we'll see how it goes. So we'll just wait for him to provoke. And I can do that.
So what is particle physics about? Particle physics is about particles. It's
all right, so let's understand that they've changed the word particle into some kind of thing that doesn't have a place or a position. It's in multiverses at the same time. It's all kinds of, it's not, why they keep cloaking their bullshit in some idea that they have this quantized simple theory when it's this bizarre theory full of bullshit. I mean, particles that turn into two wavicles, and then the wavicles interact, and then the particle somehow reforms at a location. I mean, this is not particle physics.
The question, and this is a very ancient question, at least, I suspect, about 2,500 years old, is nature discrete?
Yes, and clearly you've sided with a on the side of no. Clearly.
Discrete meaning to say not that it's polite, but that that matter and substances and energy. They didn't think about energy, but they thought about matter. That matter comes in discrete units, in indivisible
clumps, as Feynman would say.
Units, which of course the Greeks called atom. I am told that the word atom means indivisible, despite the fact that, of course, we break up atoms all the time, nevertheless.
Yes, well, we understand that the first atom we found wasn't the atom. So, yes, that was a mistake. And that the real atom, as it turns out, right, kind of interesting, there's an atom and there's an Eve. There's the electron and the proton. And in the force variety, there's the electron force and the proton force. So it does come out that you have to have the yin-yang. You have to have the white space to have the black writing. You have to have the negative before you can have the positive. And the trick is that's how this whole thing works. Like in human behavior, we're basically running from lesser conditions. We're really not trying to do better. We're just trying to run from worse, failure. The negative is the thing that runs us, the whip. And you take away the whip, and that's obviously the opposite of the whip. And that's all the reward we need, is to take away the pain. And so you don't really need anything strictly positive and negative. You just need I don't even want to get into the anti stuff, because they've turned that into a bullshit theory also. But yes, it's just pressure. And if you're rational, you understand, well, to lower pressure or to increase pressure, I have to start off with some kind of pressure. Okay, you have to have pressure to moderate the pressure. And where's that pressure got to come from? Yeah, it's got to come from the outside.
That would be the origin of the word, indivisible, that all things in the universe are made up out of something discrete. Let's call them particles. Particles is a good name for something discrete.
Just call them elementals if you want, because you don't think they're particles. So I just don't understand why they keep saying let's call them particles. Let's use the word particle when you really don't think that's what they are.
Think indivisible.
You certainly don't think that's what they are in the case of bent space. I mean, they move the same speed, they do the same thing, transfer momentum, cause things to move, and yet there's no particles in your wacky, bent geodesic bullshit.
That idea is, as I said, extremely ancient. The opposite idea.
Yes, there's not too many choices of an idea, so I'll say again, I mean, push is really obvious. All I gotta do is throw something, all I gotta do is hit it. Hit is push. Push is hitting. Alright? That's understandable. Why something moves. Now, you explain to me pull as an elemental function. There's no elemental bit to it at all. I have to have arms. I have to do all kinds of things. Just not the same thing at all. You gotta grab it with something to pull it.
Yeah, it's also ancient. Again, I don't know precisely when it was first formulated. I happen to remember a little more about the history of the atomic idea. That was, it doesn't matter what it is. Incidentally.
So he's just setting up the duality between hard bits versus mushy bits. Ether versus discrete. The difference between something and nothing, and some idea of everything being just lumps in something. Everything's something. There's just less of it one place than there is another place. I mean, does that make any sense? Or there's less of it or more of it in places. Somehow this something gets lumpy and thin. fat and thin.
Do not trust my history. And not because I don't know the history, but I sometimes tell the history in which I organize things logically.
Well, that doesn't make any sense, really. Either know it or you don't know it. I mean, either know Benjamin Franklin was after Newton or you don't.
Rather than temporally. So don't trust the time sequence that I tell you. It often represents what I wish the time sequence was, rather than what it actually was. But it's good for being present the logic of what happened, to present it in a logically compelling way rather than a.
Yes, and it's also convenient that you can use these excuses to point out how you think an experiment that was done wasn't done. That kind of thing. Like somehow you have evidence of something, and the evidence is something you made up, not something that's actually took place in history.
Strict historical way. In any case, there were these characters who were the atomists, and the opposite of them, the people who thought that matter, material, and so forth, was continuously distributed. Continuously distributed means simply not made up out of discrete elements, but I don't know what the right word is. Uniform, continuous is the right word. A schmear.
Right, a schmear. So why didn't you say the word ether? I mean, etherists and atomists. Those were the two types, and one side was decidedly full of religious kooks, and the other side was decidedly full of scientists. Yeah, the good guys.
My mother would have said a schmear. Smeared out all the space in some uniform, continuous kind of way, and we might call that the field theory of matter. Fields, what are fields? Fields are functions in space. For example, they could be the density of material in a given region of space. They could be
the number of soldiers. So he just said, this idea that you can have a field of nothing is stupid, right? That there's a field, just doesn't make much sense, in my opinion. And then it's okay, though, if you want to do that, right? You want to say there's this square of territory, and you want to call that a field, but it has nothing in it, nothing identifiable. But we know that something is in it because we know that somehow this field gets populated at a certain speed, and the stuff in it moves in a certain speed. So you have to put something in it. And then my argument would be for the two forces you know about, the most dramatic ones, gravity and magnetism, there's nothing in the field itself. If you don't put something in it, then when you place yourself in the field, there's nothing to affect you and nothing to move you. And you don't have any engine of your own that can manifest this motion. There's no energy you're providing. The magnet doesn't get lighter doing magnetism. It doesn't get hot. It doesn't do anything. So it's clearly not providing the energy. So the energy has to come from the field. So there has to be something in the field that's causing the pressure, the starting pressure. And then you just create more pressure in some locations and less pressure in other locations, and that'll cause things to move in the field. But the field has to be filled with something that produces pressure.
Electric and magnetic fields, those are good examples. Electric and magnetic fields.
There's no electric field, so whatever.
That determine how charged particles move. But the fields themselves, the electric and magnetic fields, are things that we conceive of as being uniformly distributed in space.
So uniformly, yeah, uniformly with a wavy line. It's kind of funny.
Not in the form of particles. And so perhaps matter, liquids, solids, and so forth, are also in some sense continuous, just like the electromagnetic field. That was the opposite idea. The particle idea, the discrete idea, had words like molecules, atoms, and so forth, collision.
Well, what it needs is words like force. Okay, those are the ones you should deal with. And, the consequences, matter is moved by force. The field force. The force in the field.
And particles. The continuum idea, continuum is the right word, the continuum idea had words like fields attached to it.
So I don't know why he's doing this preface, because they haven't chosen to be on either side. They're playing this wave-particle duality. They really don't even have any particles in their particle soup. They convert them all into some sort of wave function eventually, which is a wave in a medium of some kind of field. So they're basically saying ether, and they just won't. They're just such cheaters. They won't just admit that they become. It's not particle physics. It's ether physics.
Continuous fields of properties of various kinds. Which turned out to be right? In some sense, neither and both.
So, total cop-out, wishy-washy mush, bullshit, which turned out to be right, like they have the right answer, and they can't figure out what category it fits in. I mean, it doesn't make much sense. It either is push or it's pull. It's not, blah, 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 blah. This is elemental stuff, and they're just screwed the elemental part.
In some sense, neither and both turned out to be right. The subtleties of quantum mechanics got in the way of either of them being completely right, but it also got in the way of either of them being completely wrong.
So then maybe you ought to figure that you ought to change what the quantum mechanics is saying if it can't make a declaration one way or the other. Maybe you should analyze your underlying assumptions. Maybe you should go back to doing this foundational physics. Maybe you should test the hypothesis a little more rigorously. Maybe you ought to check and see if you actually did the experiments you cite that have been done. Maybe you should do some of that.
Quantum mechanics is a subtle and difficult subject.
Yes, because you can't put anything in a category. You can't actually conceptualize it rationally and reasonably because you're claiming it's doing things for which there's no explanation for how or why it's doing it.
Are many of the preliminaries of particle physics. I think I have taught all of them by now several times, and they do exist on the...
They gave all the wrong properties to the wrong objects. Slits don't do anything. Photons do everything. That kind of thing.
The Internet lectures that I've given, they're out there, and I advise you, as I said, I will try to keep it self-contained, but I am going to assume to some extent the knowledge that I have taught previously in these classes. It can be picked up off the Internet very easily. I don't know how to do it. I couldn't do it for the life of me. I can never access my own lectures, but everybody else can do it. And
so this was 2010, so, but still, even in 2010, you should have been able to access your lectures on YouTube. Not too tough a task.
Well, the real reason is I don't like looking at myself, so I never do open my own lectures. But they're out there, and they're fairly complete. There are at least 2 courses.
And, for what it's worth, I love watching my videos. Yes, they're great.
Out there on quantum mechanics. I think one on classical mechanics, at least one on special theory of relativity and electromagnetism. So, since I put that effort in, I'm now going to try...
Oh, yes, you got paid for it, so whatever. Yeah, just, since I did my job as a, professor at a university, whatever.
Draw on it, not today, but in the future, and use many of the things that I have lectured about. Okay, as I said, the particle physics question is whether nature is discrete or not. Let's just do a little bit of history, which I will probably get wrong, but that's at least chronologically. To my knowledge, the first real evidence, again, it's to my knowledge, the first real evidence that matter was discrete came, of course, from chemistry. It didn't come from physics, it came from chemistry. The division between chemistry and physics is a highly artificial one. Chemistry is simply just basically the physics of atoms and molecules.
Yes, it's very true. And biology is just another branch of chemistry.
But it came from the chemist, John Dalton? John, I think. John Dalton, who realized that the masses of chemicals, the mass of a given number of molecules, Now, how he knew that he was had to deal with a given number of molecules, when he might be talking on the one hand of hydrogen, the other hand of carbon dioxide or something, how he knew it was a given number of molecules is itself a story. Avogadro's name comes into it and so forth. The word mole, not the creature that lives under the ground, but the mole is Avogadro's number of molecules. How they knew how many molecules, they didn't know how many molecules, but how they knew how to compare different substances and say both of them had the same number of molecules, that itself is an interesting story, but it's not the story I want to tell. The story I want to tell had to do with the mass of
Yeah, I think it's a little bit circular actually, but it doesn't matter. I think the basic point is correct.
a mole of material, a mass of a given number, Avogadro's number of molecules, that it came in discrete multiples of the mass of a mole of hydrogen. Now, not exactly, but close enough to a pretty good precision. The mass of a mole of gobbledygook is a integer multiple, not three halves, not pi, not some other silly number, but some integer times the mass of the same number of molecules of hydrogen. That's
Right. So the argument is that an electron is an electron and a proton is a proton is essentially the argument. That they all weigh the same, they all create force, a force effect in exactly the same way. So essentially they have to be, can't go less than that. So in making atoms, you can't go less than adding an electron and a proton. It's just part of the game, part of the end result. And it might just be because if you have a proton, just from interactions with the world, there'll be a loose electron somewhere, looser, a free bit-ish thing, something loosely attached that will see this capacity to move to this stronger attachment and move into it. And so you'll always collect the appropriate number of electrons eventually. Some sort of argument like that. But yes, that's the basic conclusion is that they're all the same bit, and the only thing that you're really changing, the reason why you can't make a perfect statement and say it always has to be made out of electrons and protons, is because the heat changes. So heat ends up being part of mass because it's part of your movement. Your mass is basically going to be measured by the movement of the objects. I mean, that's how you measure. Weight only works when the weight your mass is moving. You can only weigh something if you can cause the mass to move. It's only when it's moving can you feel pressure from it. So you have to move them to weigh them.
sort of suggested to Dalton that there were building blocks that.
And what you're really measuring is how much force does it take to move them. And it takes as much force to move. All the electrons are moved the same way by the same amount of force, and all the protons are moved the same way by the same amount of force.
Carbon was carbon 8, carbon 12. Carbon 12 had 12 units of whatever hydrogen 1 had. Hydrogen was 1 unit of stuff, whatever that stuff was, carbon 12, or whatever the other numbers were. So it seemed like...
Right. So in those days, they didn't know protons and electrons, so they couldn't do the reductionism of recognizing what they're really measuring is electrons and protons as a pair, but what they're really measuring is the individual protons and the individual electrons as the units of mass. You can't derive substantial mass any other way except to find some way to capture heat.
Like things were being built up out of basic units, which basically had the same mass as a hydrogen atom. Almost as though everything was made up out of units of hydrogen. Dalton, I think, proposed something like that. That there were basic units, and those basic units had the mass roughly of a hydrogen atom.
So just to reinforce my point, the only way you know something has mass is you have to cause it to hit something. Move it. And then you can tell something happened. If the something doesn't do anything, it just sits there, then you can't tell what it weighs. You can't tell that it exists. You can't know that it exists. So you have to cause an interaction. And the interaction is a push. It's not a pull or some other kind of bullshit. It's something's pushing from one side or pushing from the other side, and that's what movement is. And the same thing happens to the little bits. They're being forced to move. They don't move on their own. They move because they're forced to move. There's an imbalance in the stuff hitting them that moves them.
So that was the first bit of evidence, and of course this was essentially right. Today we understand, let me just tell you why that's true from today's perspective, not to make a mystery out of it. Everything is made out of atoms, and atoms are made out of protons, neutrons, and electrons. Electrons are very, very light compared to protons and neutrons, and in counting up the mass of an atom.
So let's understand that the difference between the proton and the neutron is the fact that there's an electron, the very light thing. And that's really the difference. So the neutron isn't neutral, it's really a magnet. It's really a dipole. It's just that the dipole is spinning or doing something that hides its character from you. But from a distance, and that's all you can see it from is a distance, it's going to look neutral because it has just as much positive as negative charge, and the two charges are so close to each other that at any distance it's always going to look purple. It might be made out of red and blue, but it's always going to look purple from a distance. And we can never get close enough to see the red and the blue until it degrades, decomposes, and falls apart. And then we see the electron and the proton.
The electrons are not very significant. An electron has about a mass of 1/2000. 1/2000 of the mass of a proton or neutron.
So again, that's just how much force it takes to move it, and again, how you're moving it depends on how you've isolated it in the first place. It's really hard to isolate an electron or a proton from force, from already being in some field that you're keeping it from going somewhere, keeping it from any influences. And that's already hard to do, so it's pretty hard to measure anything's real mass. And certainly its rest mass, I could argue, is impossible to really measure. Because, again, the only way you can measure something is to have an influence, an impact from it. It has to move. You can't know its mass any other way.
So electrons don't come into the equation. They do come into the equation, but only a very, very small term. Forget about them. Protons and neutrons constitute most of the mass, almost all of the mass of ordinary material. On the other hand, protons and neutrons, surprisingly, there's no reason.
So again, the simpler way we measure mass is just to measure the effect of gravity has on an object, and we know that the gravity is absorbed proportional to how many bits are inside the object, and so everything different weights, different atomic weights will merely absorb more or less by the same kind of atomic ratio. The electrons and protons will absorb energy, create less energy going through it, and mock gravity, and the result will be a proportional amount. So more force will be absorbed by the heavy thing than the light thing.
Reason for it, but at the time there was certainly no reason.
And by more force, I mean it takes more force to move more things. If you have more rocks to move, it'll take more force to move the rocks. The rocks won't move any faster. It's just that it'll take more force to move a pile of rocks than one rock. Obviously.
In fact, protons and neutrons weren't known, but protons and neutrons have about the same mass as each other. As I said, about 2,000 times the mass of an electron. And so the mass of a molecule is basically the mass of protons plus neutrons. They have about the same mass, and therefore the mass of a molecule is an integer multiple of the mass of a proton and neutron. On the other hand, the nucleus of hydrogen is just one proton, and so it did turn out that Dalton was right. All materials have a mass which is approximately, there's an approximation in there. Protons and neutrons don't have quite the same mass, slightly different. Less than a percent, incidentally, 0.1%.
Well, hydrogen gets complicated because hydrogen in nature doesn't really survive as a single hydrogen atom. It's always in the form of a molecule of two or more hydrogen atoms. And, there's reasons for that. I mean, it's more complicated. The single atom becomes kind of a bigger single atom. In its natural condition. So a hydrogen atom isn't really that simple because in most cases it's more than one atom stuck together.
Even less. Whereas electrons are so light that they don't come into it very much. And so Dalton was right. And it was to my knowledge, the first real evidence that matter came in discrete units. Now, molecules were in atoms, of course. Took a little while longer to find out that molecules were made up out of atoms, and the atoms weren't just protons and neutrons or hydrogen, that atoms themselves, the things we now call atoms, that there were about 100 of them, 100 different kinds. This was, of course, a great...
Right, and they ought to have clear words for that, you know, so unfortunately they don't have a clear word that tells you this is a pure element, okay? It's like hydrogen. Hydrogen is in this form of two atoms stuck together. There's no like word for that, like where you'd say a molecule versus a compound. Instead, molecules can be a molecule of a compound, so it's a mixture of different atoms. And so it'd be good if they had a word that just described when atoms stick to each other, all the same kind of atom sticks to itself and forms different. It's mechanically different. I mean, clearly carbon's mechanically different in the form of graphite and in the form of a diamond. You know, huge difference. And it just has to do with the arrangement of those atoms in a molecule. But the molecule doesn't have something else in it.
History of the 19th century and early 20th century to identify all of the elements that go into the periodic table up there. Incidentally, the periodic table is not very periodic. You know, if you really look at it, it's a bit of a fake, the periodic table. It's not very periodic. But nevertheless, identifying all those separate atoms up there, the elements are some things which are composed of all the same kind, you know that story, composed of atoms, and identifying the atoms, and at the end of the identification of atoms, roughly about 100 of them, less than 100 occurring in nature, 92 of them to be precise. Well, more than that if you include isotopes. But order 100 different kinds of atoms, and everything made up out of it.
Right, so we all know this stuff, so blah, 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 blah. And yes, the periodic table could be better. It's not very easy to follow.
Atoms. So atoms, at the end of the 19th century, the things we call atoms or elements were the building blocks, the elementary particles of nature. Now, of course, it took another 5 years after the turn of the century for Einstein to do something that nailed, really, really nailed the molecular theory of matter. It wasn't until 1905 that Einstein explained in detail how you could prove that matter was really made out of particles. But long before that, chemists, physicists understood, for the most part, that the...
Well, frankly, the proof is sort of, I mean, I agree with the conclusion, but you can argue that they've kind of exaggerated the proof of, both the ultraviolet crisis and the idea of electrons being ejected by a minimum amount of energy. Because, again, your measuring device is the one that's really deciding what you're going to be able to see or not see. So in a sense, if your measuring device can't see anything that's smaller than something, then it's always going to see it as a clump. If there's a minimum clump your measuring device can detect, so it automatically clumps things, okay, that might not be clumps, because it can't detect anything smaller. And, that's sort of a catch to this conversation. And I guess I would argue that it's part of the catch that also leads to this misconception of photons as a entity in themselves. Like a photon would be just one round cannonball, like that's a photon. When no, it's got to be considered as bits that make a length that makes a photon, a length of little bits. And you have to understand it's a ray length. And what makes something opaque isn't so much that, well, that's something I probably should draw. So maybe I will, maybe I'll do that. I will switch to the drawing board. To the drawing board and such. Alright, I'm back. Pretty much, for the most part, close enough. Gotta get the cap off the damn marker. Anyway, so I never really saw any analysis where in physics they did any work to have a conversation about this idea of a photon. And they make it this thing and they say it has this wavelength and it has a frequency, and somehow that's built into one clumpy thing, when it seems the obvious way to understand the photon is that it is just this. So again, this idea that the photon is a thing turned into this this wave crap, where they gave it two waves, one going this way and one going this way. That doesn't get you anywhere. Particularly interesting in the sense that it's not, in my opinion, it's not something you can understand. Why would it be doing any of that? Why would this and field of electric field vibration and magnetic field vibration, yet there's nothing magnetic or any of that stuff. So I just haven't seen too much discussion about this idea. The photon's a thing, a clump of photon, that somehow this would be a thing when it's a bunch of waves. It's obviously coming in pieces. So in a sense, this sort of looks like, that you could quantize it and say there's an element to the photon, that would be one wavelength. But the problem with there's a lot of problems with their drawing. So you could think of it as things attached to each other, but they don't even have that conversation. And that this would be the wavelength, okay? But they don't really have a conversation about ray length then. When this would still be a ray, right? This is obviously more ray-like than, this. And they still just don't have that conversation. When I say, this is how I've always thought of the photon. I mean, since I was a kid, the only way I could make it make sense. Well, and this is your wavelength. Your wavelength is just, if you count from the front of this one to the front of this one to the front of this one, that's your wavelength. Your frequency is the amount of time these things pass you at a given point. How fast they pass the given point is their speed, the speed of light, and that they're clumps of momentum, and same kind of momentum. They're little hits. And the trick is that our test instruments can only detect, they have to have a minimum number of these things to detect them as a hit. And the idea is that an electron has to be hit by a certain number of these things, a minimum number, and a certain speed. That is, they have to be close enough to each other to kick, to kick the electron. So you can't kick it. You can't kick it out of its tension. It's captured in an atom, and you can't force it out of the atom unless you hit it at a certain speed. That was what was found out, is that this frequency, that means this wavelength has to be small enough, where you're hitting it often enough in time to do it. And the reason I'm arguing that's true is because of the rebound. The electron is in a position in an atom, and it's locked in that position by tension. It has tension with the other electrons and the proton in the atom, and it has to have a certain momentum to escape, an escape velocity, essentially. And the problem is when you hit it, it tends to go back. So it has a rebound tension. It's in a field, it's getting hit by forces that keep tension on it. So when you move it into the force fights back. And the trick is you have to move it faster than the kickback force will kick it back. And then you can get enough speed to kick it free. So it's like a ball on a string. If you kick the ball hard enough, you'll break the string. But if you don't kick the ball hard enough, it can't break the string. And the hardness comes from how fast you hit it, how the speed of the frequency. Now, I would say this model fits the evidence and does it rather completely in understanding that this electron is in tension, it's being hit by other little balls, they're coming at a slower speed, all right, ER, than this frequency that you have to put in. You have to put in a frequency that's faster than the force coming back this way to be able to kick it free. Alright, so that's part of the explanation. So what's been learned, what I have discovered over the last couple of weeks, is a better understanding of the electron, in the sense of that perfectly fits their quantum mechanics, in the sense of it explains why the electron appears not to have a fixed position in space. And the idea, as I've pointed out before, is that the electron sort of has to be understood as no matter which way I orient it, there's always the three dimensions, okay? The two dimensions perpendicular and the in and out dimension, however to draw that. So you have the three dimensions. It doesn't matter which way they are, they're always oriented the same way, where the two dimensions are always, the perpendicular ones are 90 degrees parallel, 90 degrees perpendicular to the other dimension. So any one dimension, the other two dimensions are on the same plane. And so if you're moving in one dimension, well, the point is you're going to end up moving in all the dimensions. So the point is that any hit, like say getting hit this way, we kind of understand that has two components. It has a component this way and a component this way, from this perspective. And everything has that perspective. So if I rotate our perspective, then this arrow will be just this way. And I'll be able to understand the three dimensions, and perpendicular that way. And so, but in the real world, the three dimensions there's no preferential dimension, there's no, so it's always from its point of view. And so from its point of view, at any one time, it's getting hit, I would argue. It's being hit by pressure from all directions. And you can sort of understand from all directions means in these directions also. And it's essentially, at any one moment, got more momentum one way than another way, another way, another way. And if you cut it into three pieces, you'll see that it has a component of movement. All right, so if you fix a dimension on it to measure its movement, then you'll be able to say, yes, well, it's moving this much this way, and it's moving this much that way, and it's moving this much in or out. At any one tiny Planck constant of time, that's what it's doing. That's its orientation based on what it's getting hit by. All right, I think that's somewhat understandable. I don't know. So the trick is that it's never stationary, and the reason is because of this exchange thing. So the important thing to understand is the electron exchanges energy. So it already has a bunch of energy inside of it. It has a bunch of pressure, a bunch of little bits, and it basically, when a bit hits it from the outside, it exchanges this direction for the opposite direction, essentially. And so something this way comes out. So I would erase that and add that. And so now it has a bias in that direction, which combined with whatever biases it has in the other direction will end up with some kind of net direction. So it has a net movement that's based on what's influencing it from the three dimensions. So the three dimensions are totaled up inside the electron. Essentially, the math is done, and there's a net movement that's based on whatever biases it has and whatever exchanges it's made with this external force. So any change to the external force obviously changes the motion of the electron. Now this only works for the electron force. The proton force that also exists in the universe doesn't affect the momentum of the electron. It just changes which way it goes. So it just goes in and goes out. So it might be 15 interactions that cause that, but the net effect is that the exchanges are done and nothing happens except the direction of the little force bit is changed. But the electron doesn't gain any momentum from that interaction. It doesn't change any of the people in the seats, stay the same through the process of ejecting the red guy. The red guy kicks out, and it's like they never made any seat exchanges, but he gets kicked out perpendicular. So he jumps in the front of the boat, and he gets kicked out of the side of the boat. It's essentially the analogy. He's just pushed. If he's coming in this way, he's just pushed that way. Where these black bits do this exchange thing, which causes the electron to move. So obviously every electron is never stationary, in the sense that yes, it does. You can say it has a fixed position at a moment in time. That is, a moment in time would be the distance of those little force bits. That would be your Planck moment, would be how much time it takes for this bit to get to this spot. This tiny distance between the average distance between a force or something like that. The minimum distance between a force, doesn't really matter what you think of it as. So at any one moment, you could argue we could make a moment small enough where the electron won't be appearing to move. So if we made that moment, it'll be in a position. But the fact is it's on its way somewhere. So it has a tendency that it's going to move somewhere in the next moment, the next impact of a force. So you could just say that the forces are stacked, and that each one will happen at a different moment. Two can be coincidental. I mean, you probably have two force bits hit at exactly the same moment, and they'll just do the obvious thing of add up to that kind of action. So the next moment it's going to be in a slightly different position. It's just impossible essentially for it to stay in the same position, because that would mean it would have to make exactly the same exchanges in the 3 dimensions in the next moment, and it's probably highly unlikely. At any rate, highly unlikely that it would ever stay in the same position. Now the trick is that any momentum I give it, any change in position, so it can change position, but the native state would be it would just keep changing in these little ways, just change in an area, and it would have an average area. This would be the highest probability by how they describe it. So this is just a mechanical way of describing the fact that something can have a probabilistic location, and you can understand it's for physical reasons, though. It just has to do with how the force is around it, and the fact that it's a randomized force. It's not purely random, but I'm just saying it's random enough where at any one moment it's going to have to go in every direction. Because it goes in any direction, it'll have to eventually go in every direction to be considered naturally random. However you want to put it. I'm not arguing there's a true random. I'm just arguing that obviously things have so many variables that it appears random. All right. So the idea is that if you gave so this is the irony now. So Richard Feynman argued that there couldn't be mock gravity couldn't work. The idea of a field of energy pushing things together couldn't work because of this drag issue, that if I made something move through the field, that it would be dragged to a halt, in the sense that if particle gravity was true, the Earth couldn't keep its velocity around the sun, because as it moved, it would hit more stuff going in the direction of its movement than it would hit, from behind it. It would appear there was more force ahead of it, because it would be running into it, getting up to it sooner, collecting more of it. And the truth is that's exactly how electrons behave. So that's sort of an irony that Feynman should have realized, is that that's exactly what electrons do. They lose their velocity. They decelerate because they're making these exchanges. So if I hit more coming forward, that means I make more exchanges forward. I lose, I give away more arrows forward. And, the object itself decelerates. It's going to lose its acceleration, but it's always going to be knocked down to 0. And so that happens in all dimensions. So all the time, any velocity an electron gets, it will be destroyed through a deceleration. So in a sense, you can only accelerate and decelerate an electron. It never has something called a velocity. It never just travels peacefully from one place to another. It's always accelerating or decelerating, essentially, because there's always field that it'll hit more of or less of as it's traveling. So that's, again, fits perfectly the evidence of what electrons are doing, and it makes it understandable that that the drag is real. And so now it sort of says that we know that this is another piece of evidence that of the of the mock gravity being correct is the fact that yes, drag is a real thing, and obviously you could argue that big matter that's full of more bits is doing something that electrons can't do. It's overcoming drag to maintain a velocity. That is, there has to be something in bigger pieces of matter, like a helium nuclei, where it has an engine. And I've sort of described what that engine would look like, which is something like, you know, an electron and an electron, and then just sort of leave the cap off, save myself trouble. And then you have a proton here, and if you understand that the black force is just goes perpendicular, so imagine these were 90-degree angles, which they're not, but you know that this is a 90-degree angle. You can sort of understand that the force, this force always reflects off the black things, the electrons, and it just moves perpendicular through the proton. So you'd have a constant pushing this way, okay, and no pushing this way. And so it'd be like a little engine that could, and it'll just keep this thing moving. And this is a pretty close, this is a neutron right here, essentially. So all you need is this extra electron to make it work. All right. So what else? There's some other bigger consequence to this whole thing that I wanted to get to, with this electrons vibrating. It's key, important in some other way that I'm not remembering. So really what you're talking about is the electron's always kind of wobbling in a position. And the idea of kicking it out means that you have to give it a velocity. And when you give it a velocity, the one key would be, another point to be made is that if you keep hitting it in one direction and changing its bias, so that is, you keep hitting the electron with a lot of, you know, quick force, so then it's like it's decidedly got a lot of arrows in this direction and very few arrows in the opposite direction, because it made lots of exchanges this way, okay, and fewer exchanges the other way, because you sent a lot of force this way, and just the average amount of force was coming this way. So you made lots of exchanges, you gave it faster and faster momentum. The faster the momentum you give it, the less exchanges it's making in these directions. So in a sense it gets straighter. So it's not wobbling as much as you give it faster and faster velocity. It goes in a straighter and straighter line. And I would argue that eventually, if you get up to the speed of light, you've essentially turned it back into force itself. And all these arrows will be just all going the same way. And all you've done is changed the electron into a clump of force. Yeah. Okay. So that's part of, there's something else though. Let's see if my notes are around. All right. Oh yeah, I wanted to get to the photon breaking part. I found this kind of interesting as a theory for why substances are opaque that still seem to have very few. I mean, the odds of hitting an electron kind of thing seems like it's very improbable that you would hit one. So let's say you have this photon coming through and it's at a certain frequency, and we have the option of making that frequency smaller, I mean closer together, and you're going through a substance. And so if you understand that the electrons aren't in one position, the idea is that this electron now isn't just this one little thing that you have to hit, in the sense that each electron is moving in this field, and it's moving, so it's essentially in all these locations at some point, right? And the idea would be is if you're sending your photon through, now the electrons are much bigger in a sense, because the electron could be here, could be here, could be here, could be here. I mean, at any one time it's going to be in all those locations. And so the idea would be is that if your photon is so far apart, if this distance is big, all right, then one of them goes through and the electron was over here. And by the time the third one gets here, the electron's here. And so now it hits it. So two of your photon got through, but the third one, yeah, it's crashed right into the thing. So the third one didn't get through. It moved the electron instead, and it didn't get through. And so you've broken your pattern. So if you had a pattern of, say, you needed 6 of these for us to see it, you need 6 in a row or 5. You can kind of understand that, if I take this one out and I need 6, I'm not going to see the energy anymore. It's not going to be a photon anymore. My eye won't recognize it because it's not going to be able to hit that electron. It's not going to be able to move it enough to cause an electric flow. That is, it's not going to move it enough to affect the atom next door. And so you have to move this electron in one atom enough to bother the electron in the other atom and cause it to gain the pressure, and that's how the electricity is moved. So you don't have the minimum enough force because the electron, it got momentum, but then it lost a little, and then it got some more momentum, so it ended up back where it was. It didn't end up going far enough because it didn't get enough. It's missing this key bullet. You need this key bullet to get this electron out. And so that's what makes substances opaque, is the fact that the electrons are moving more, maybe, and they're breaking the photons. And so that's why the photons can't be seen coming out the other end, is because they've been broken. And in this form, they just keep bouncing off there's another electron here moving, and so by the time it gets to this one, it gets broken even more. And with each break, it's reflecting the opposite direction. So the photon was going this way. When it hits an electron, the photon will come out this way. The piece of energy will be going the opposite direction. And so that's part of the game being played here, is that it starts bouncing inside the material. So the whole material heats up because the electrons getting cascaded between the electrons and just bouncing back and forth, trying to go this way, and it just can't go that way because it keeps hitting something that forces it to go the other way. And the end result is the thing that we saw as a photon is going to be missing too many pieces, and we're not going to see it as common visible energy. But the energy still radiates from the material. Eventually it gets out of the material as in a form of the edge of the material, as I pointed out, is full of electrons. So the edge of the material's got a bunch of electrons on the outside. The electrons are on the outside of the atom, right? That's just accepting the standard model, which I don't think is wrong. It's wrong about the orbiting, but it's not wrong that the proton's in the middle and the electrons are on the outside, essentially. So any substance will always have electrons on the outside and protons sort of protected back here. Call the Xers protons. Anyway, so the point would be is when these things all vibrate and you hit an electron, you give it a little bit of a push out. You're going to push it out of the substance, and it's going to reflect back into the substance. And when it reflects back in, that's when it's going to emit the energy we see as a photon. So it'll just, because of how far you push it out, and so it's going to move back. And what does moving back require? Moving back requires that there's less force this way, more force this way from the external world, and the electron is basically going to do these exchanges, where it's going to exchange a rider, and exchange a rider, and exchange a rider at the rate of the force that the matter is pushing it with. So whatever rate this force is, however strongly force is coming out of the atoms in the material substance, that's going to decide the wavelength here, because the electron's going to move based on, it's going to slow down, coming back, slow down, wrong word. It's changed its direction. It's going to be coming in based on the standard force of the field out here combining with the force here, and that'll tell you the rate or the frequency, okay, at which these exchanges will happen as the electron moves this way back to the matter. I guess that's the way to say it. So the swing back will be dictated by a combination of those two forces, and this is mostly what we end up seeing is some variety of infrared radiation, which says that's the average tension in the average atom would be infrared, since it's the common bit of energy we see that comes off of something that's hot. But obviously you can make something hotter and change the color of the light that comes out of it. You can change it to visible light, and then eventually white light, and then eventually you make it hot enough, I guess X-rays will come out of it. All right. So I thought that was interesting, just the idea that you can sort of understand that photons go into something, and if the geometry of the substance is some special geometry, the idea is that the photon doesn't get broken. The energy sequence stays intact, and it moves between the atoms and comes out the right way at the end over here. And that's a transparent substance. And non-transparent substances are just eaten up by the vibrations of the electrons. The fact that the electrons appear from the slow moving, these are kind of slow. You're talking about nanometer distances here, which are pretty huge. I mean, the atoms are much smaller than the width of the wavelength of the photons. So the wavelength of the photons is much bigger than the size of an atom. Atoms are smaller than that wavelength. And so you have to understand that a million atoms fill that. And so you have lots of little electrons vibrating, in that little tiny bit of distance. There's lots of action happening, lots of movement in the same amount of time that it takes an atom to move. This is moving a lot in that same amount of time it takes from one bit of a photon to get to you and another bit of a photon to get to you. Okay, anything else? So sort of another argument that gets to gravity a little, like why is magnetism 10 to the 40th times stronger than gravity? Well, that goes back to another spacing argument, right? I mean, in the Earth, the electrons are, the thing reflecting, the mirrors, are separated by tons of distance. I'm not even, there's no way for me to even draw the distances. Okay, so when gravity's coming in, these electrons are spaced with a lot of empty space, right? And so the mirror, you would call these the mirror bits. The mirror is really, it's not half silvered, it's 1/millionth silvered, it's 1/billionth silvered. It's a tiny amount of silver on the glass. So only a tiny percentage of the glass is a mirror that will reflect something back straight, right? And the other thing you have to understand is these mirrors are moving in different directions, so they won't reflect back accurately. They'll reflect back in some other direction because of the net idea, where the actual electrons, if they're face to face, if two electrons are brought in proximity to each other, you can understand that there's no missing. Okay, everything's between them, and there's no empty space in the electron. Now the movement part has to be accounted for. They are moving, so they can miss each other in some ways, and so I have to explain that eventually. But the point is that whatever bounces between them, all right, is always going to hit the mirror. It's not like there's a bunch of empty space inside the electron. So the 10 to the 40th, problem is really a description of the difference between this full mirror and the amount of mirror you have when you have electrons in atoms. It's 10 to the 40th difference in the amount of mirror that this reflection is going to hit. It's 100% going to hit this one here, and it's only 1 times 10 to the 40th, okay, chance of reflection when it's hitting the big object. That kind of thing. Anything else? It sort of makes sense that the elemental bits that are actually causing the effect, the motion, would have to be hugely more impacted than the thing that has all the little bits with a whole bunch of empty space. I mean, it's really 10 to the 40th is just telling you how the difference between the empty space between atoms, from atom to atom, is 10 to the 40th space. There's more space by 10 to the 40th than there are actual little bits inside an atom. So that proportion is essentially telling you the strength of the force. Alright, probably enough. So we'll play a little bit more, and we'll probably make 2 or 3 videos. You know, we want to get a bunch of 2-slit stuff, you know, in the next video, based on what Susskind says and such. You know, the standard crap that I will debunk, because it's crap. On second thought, decided I'll call this the end of this video, and we'll just make another video on another day, going through the same stuff and such. Continuing. Yeah. Just explaining how, look, all they do is change their rhetoric a little, their concepts a little bit, and you have the right theory versus the wrong theory. And again, I'll just point out the Feynman argument. Feynman's arguing there's drag would be a problem, when, like I said, all the evidence points to electrons are affected by drag. So Mach gravity's back in if you understand that clearly that's what electrons do. They decelerate. If you don't keep forcing them to move, they'll stop moving. They don't maintain a perpetual velocity. And that should have been something Feynman would have realized, I think. He should have. Anyway, save recording, and till next time, such.